Good afternoon, everyone. My name is Robert Hirsh. I'm with NASA Johnson Space Center, and I'm here today to talk about the data definition management that we used on the Orion Backup Flight Software system. And get my slides started here. So the first thing I'll do is sort of give some background on the Orion Backup Flight Software project itself, Core Flight Software, CFS, and the CCDD. And again, after that, we'll get into some of the interface management work that we did on the BFS program, and then how we did distributed CCDD management using the JSON file format, and then just some of the products that we produced on the BFS program using the CCDD, and then some future steps. Okay, so begin at the beginning. What is backup flight software? The Orion Multipurpose Crew Vehicle has a backup flight software system, or BFS, and the basic purpose of this system is to reduce the risk of losing the crew if something happens to the primary. So if there's some weird corner case divide by zero error that causes the primary computers to fail, the BFS team has a completely separate operating system, hardware, software, philosophy of how we build it, and also the developers who built the code. So we're trying to minimize the chances of a common cause failure. This is similar to the concept of BFS that was used on the space shuttle program, except that system actually ran on an identical computer hardware as the primary system. So we're even more dissimilar. The BFS team decided to use the CFS architecture. So like a lot of projects that are here at the workshop this week, it's a fairly common system, and I'll cover it a little more on a future slide. But that is not the same that the primary is using. Where BFS is less complex than the primary flight software and much less automated. It leaves a lot more responsibility to the crew and ground to basically issue a command when they want it executed. So if they want to open a valve or turn on a fan, they send a command to do it at the time they want it to be done. And so it's a much simpler system, and therefore hopefully less prone to errors. And basically, BFS acts as a hot backup during dynamic flight phases. So your ascents, burns, and entry. And that's basically times where the vehicle is going to need to issue commands sooner than the primary could conceivably reboot. So if there was an issue, we're in a quiescent period where not a lot's changing, it can take an hour or two. And as long as the crew has oxygen, they'll be fine. They'll just sort of coast along the current trajectory. Whereas there's certain phases, like when you're doing entry, if you don't issue a command, the vehicle will tumble and crash. And so you need to be able to issue commands to keep the vehicle stable immediately. And so that's why BFS is especially critical during those times, because it's sending out commands all the time. And basically, as long as any of the primary computers are up and active, BFS just gets ignored. So it kind of like if you've got a video game that you're playing with your younger brother, and you give him a controller that's not even plugged in. He thinks he's playing along with you, even though he has no control and can't do anything. BFS is, pushing buttons and trying to do things, but as long as primary is there, it just all gets ignored, and so we're not able to do anything. But if at any time the primary goes away, BFS is able to instantly take over, and the commands start getting listened to. BFS is a joint Lockheed Martin NASA development team, and it's very distributed, across the country. Which served us well in the era of COVID, because we were already sort of used to doing virtual meetings and telecons. Anyway, so it's a great team to be a part of. But the underlying thing with BFS is it's sort of unique in flight software. We're hoping that our code is never used, because a lot of things have to go wrong in order for BFS to ever take over. And so even though we're working very hard and trying to make sure that there's our software is good, we're crossing our fingers and hope that we never even have to find out if our software will work, because the primary stays in control the entire flight. So CFS, this is something that a lot of people are probably familiar with. Core Flight System was developed by NASA Goddard as a reusable software framework, especially targeted toward spacecraft, but applicable to ground systems as well. It's freely available. You can go download it there at the link, and it has been, is, and is intended to be used by many projects. I have a list of several of them there, but there's a wide variety of systems, from actual missions going around the moon to flight demonstration projects to the Orion BFS team. The CFS, however, does not specify that you even have to use a command and data dictionary, but realistically, any flight program is going to require some form or shape of a CDD, just as if nothing else, as a documentation. Because if you're going to be flying a spacecraft, somebody's going to want to know what commands you can send or what telemetry you get back from the vehicle. And the format of that, is certainly varies from project to project, but it needs to be done. Again, this could be done as something as simple as a spreadsheet. Maybe you have some utilities that output that in some useful file format. But the problem with making a custom, utility thing for each program is that it limits the ability to reuse between different projects. And a lot of projects are, somewhat proprietary about their systems and their data, and so they don't want to have tools out there, for export control reasons. And so, but I think trying to use a generic CDD utility will help minimize the duplication of effort that's done on an individual project and able to leverage work that's already been done on previous programs. And that brings us to the CCDD. So the CFS Command and Data Dictionary, or CCDD, was designed as a generic way to eliminate duplication of effort in order to maintain and manage the CDD on a CFS program. Again, it's an open source project. You can download it at the link below. It was written in Java, so it's portable. It can run on Linux, Mac, and Windows. And basically, it stores all the information, all the CDD information for a CFS program into a Postgres database. That's a SQL database that's freely available that people can use to store information. One of the limitations for the CCDD is that when it's accessing a database, it's limited to one user at a time. And so you can't have multiple users in changing the database simultaneously, just to prevent issues of stepping on each other and doing that sort of thing. That's not such a problem for a small program if there's only one or two users. But if you get a larger team, that does represent a serious bottleneck. And that was one of the things that we wanted to address when we first started the BFS program. And we'll talk about this in a little bit, but we moved to a distributed development model, which allowed all the users to be able to make their updates and changes locally, and then check it into our Git repository. And then we'd have one user that would take that data and put it from the Git repo into the CCDD. So it allowed everybody to independently develop and work and manage their own individual tables for the database, and then only have one user to actually push to the central database. So some of the goals of the CCDD were to be able to allow people to easily create and modify their CCDD information. So it's a graphical user interface that you can, kind of looks like Excel. You can have cells where you enter each piece of information for all the columns and rows of your data. And again, it's compatible with Excel. So if you've got an Excel spreadsheet that has some data in it and you want to copy and paste, you can do rows and columns simultaneously, copy and paste it into the CCDD. And you can also import and export to files. So XTCE, JSON, or CSV files are languages that are spoken by CCDD. And CCDD also allows easy access to the information to your own scripting language. And so if you've got a particular file format that you want to create, or some kind of thing that you want to generate, you can write your own script in one of the common languages: Ruby, Python, Java. JavaScript, so that you're able to make your own program, write your own script that will have access to all the information in the database and be able to output in whatever file format that your team decides that they want to use. And you can do things, for actually generating code. It could be data summary, or if you had to have some kind of report that you needed to turn in, anything. It can be a HTML file, or a .h file, or a Java file, or a Python file, whatever kind of format that you need. You just write a script that outputs in that format. And you can also generate some complicated CFS programs, products. So your scheduler, network tables, the HK copy table, those sorts of things that are need information about a bunch of different applications. It's able to grab that information out of the database and then generate that high-level product automatically. And here's just sort of a graphical picture of how we're using the CCDD on the BFS program. Bottom right, you can sort of see the database, that Postgres in this little cylinder here, and then the CCDD program, interfaces with that database. That's the only thing that actually talks to the database. And above the CCDD, you got that script accessor method. So that allows the user to have external scripts that talk through this interface to be able to access the database using the CCDD. And then again, you can output whatever file format you want, ITOS, C header files, display pages, anything that you need can be generated if you write a script to generate it. And then you have the direct import and export things that CCDD supports. So you can use the clipboard, just copy and paste directly in. You can use XML files, EDS or XTCE, JSON files, or CSV. So you can just import and export via file. And then there's also a web server that CCDD supports. So you can use a web service to talk to it using a web application. So that's sort of the ways that CCDD can be interfaced with. And again, it's just storing or helping to store the data in the database. And in addition to the table data for each message that goes on the software bus, all the bits and bytes of those messages, there's also ancillary data, it's like your MSIDs, GUIs, comments, for your code, units, all that sort of stuff that can be stored for each parameter. It can be stored for a table. We initially started this with the EM1 BFS flight software structures that we were being used back in August of 2018. We actually had an intern who was here over the summer, and so as part of his work, he just basically imported everything that was currently in Orion BFS, all the messages that we were using, and put those into the CCDD. And EM1 is much a simpler version of the BFS system than EM2. There's a lot more applications. I won't get into the specifics of those, but there's a lot more capability and functionality that's in EM2 than there was in EM1. And so the BFS applications, the new ones that have come online, have now had all their messages and tables defined for the CCDD. Again, I mentioned we can import and export all that as JSON, and that's sort of the file format that we chose to use on the BFS program. And so we take all the information that's in the database, export that to a bunch of JSON files, and then those JSON files are checked into our Git repo, just as any other kind of file. And so it's configuration controlled and monitored that way. So we're able to see who's making changes to tables or when or why, and all the stuff that you get with your version control. We get that because we're breaking it into JSON files and storing those in the database. And then we've written scripts to output information that's needed for different pieces of the Orion program. It's amazing how many different people are working on the ground data system for Orion and the different kind of file formats that need to be done. And so we've been able to start working on and making the files that we need. Again, we started with the C header files, the data table files, the HK copy tables, the scheduler tables. There's a bunch of different files that we're generating. So just to go dive a little bit deeper into the JSON files, every structure that's stored in the CCDD in the Postgres database is defined by a single JSON file. So there's a different JSON file for each table. You can sort of think about these like a base class definition in C++. So if you define a structure or a class, and you get one corresponding .h file that defines that. Atomic types, so things like integers, floats, doubles, those types are stored directly in that parent JSON file with the where that structure is stored. If a structure happens to have substructures, it basically just references those and says, hey, this data member, instead of giving all the information for it, it references the file where that substructure lives. And that's stored in its own separate JSON file. And I don't know, it's a little complicated. Maybe I'll get to that at the bottom of the page and sort of give an example. But there's a separate JSON for every instance of every structure. And so if there's a particular structure, like for instance, this in cyan at the bottom, the CFE software bus telemetry header, that's the common CFS version 1 header, 12 bytes with the CFS header and then a 6-byte timestamp. That is used by virtually all of our telemetry apps. And so we define that structure once, and then every place it's used, it basically just references and say, hey, I need a telemetry header here. And then that it doesn't have to go in and define what that structure is. It's a reuse of the base class. But you have to define that because each of those different telemetry headers might have specific values, for instance, for the message IDs that are embedded inside. So you have customized data for each one of those instances, but the definition of the data structure itself is shared. And again, all those are shared in their own instance, is what I'm calling it, JSON file. So each CFS software bus message is defined individually. So again, the parent has the information about the message ID, the rates, et cetera. And so in the example below, that we have our BEX HK telem SB message. And that has two direct children, the cyan telemetry header and that purple, the telem PID. So those two structures are all that's inside that BEX structure. And the purple one, or magenta, actually has one substructure inside it. So it sort of has a grandchild of BEX. So it has a child that inherits another child. And so you have these four base classes. So you've got the BEX HK telem, the CFE telem header, the BEX HK telem PID, and the BEX HK telem PID. So those are the four base classes. And then there's three specific instances. So you've got, for instance, this BEX HK telem, CFE software telem header, and then a particular instance. And so this file here is basically this specific instance of that file. And again, this one here is this one, and this bottom one is this green system. And so these are the specific instances. So this one message that's sent out on the software bus, there's well, this one's sort of shared by many different apps, but there's these 7 files that all describe this one message. So it's very compartmentalized. And you're able to make changes individually to those tables without conflicting with others who are making changes in their messages. Because you're only, for instance, if you're the app owner for BEX, you're only making changes to these files. You don't have to worry about changes that somebody in guidance or control or nav is making to their applications. You're able to make your changes independently. So trying to determine what form of configuration control to use for our database was a big issue we spent some time looking at. Initially looked at trying to do the entire binary file as a single file, but it'd be sort of like configuration controlling a JPEG file. You can do it, but it's not really as useful as you might think. It's hard to tell changes or regress them. Also looked at doing a single DBU database text update file, but again, there was still some issues with non-determinism and also just huge changes that could be done by renumbering. If you added or subtracted an item from a table, the indices of all the later items would change. So you'd get mass changes when you really hadn't done much of a change at all. So ultimately what we landed on was using a series of JSON files, each one to describe one table in the database. And that does make a large number of JSON files, but each file is very compartmentalized, and so the changes for that table live in that JSON file. And it allows people to work on different parts of the database in parallel without having merge conflicts, as they're each able to work on their own JSON files. And it allows, because we're using Git with all of our databases, each of those individual JSON files is tracked by the author as they make changes to each individual file. And so it keeps an easy way to track who's making changes and why and where. And then after we have that database defined, the directory defined with all those individual JSON files, one CCDD operator can pull those results and push them into the main global database. And so our database is only updated can be updated out of those that Git repository directory. And so we're able to pull in those changes from all users and push them into one central database. So some of the things that we produce on the CCDD for BFS, those JSON files we were just discussing, those are produced by the CCDD. We generate all the header files that we use for our software bus telemetry messages. We generate the message ID file that we use to define all the MIDs that are used on the host computer. Generate that Frankenstein HK copy table message that basically lets you conserve telemetry. And then a DPM file, which is basically the same idea, but specific format that needs to be sent to the onboard displays for Orion. Configuration table management. So we're trying to store all the data that's used by every app, as well, our custom apps, as well as the core apps like Scheduler or DS. And so part of the effort that Orion is going through is trying to validate every parameter that's used anywhere to make sure that none of those tables have an incorrect value in them. And so we're having to go through and do a validation effort exercise where we're going through and identifying each item in each table, when it was made, how the changes were made, and why, so that we can know how that's being done. And so that new process is all being handled in the CCDD, so we're able to track that information just as an extra column's worth of data in the database itself. Some things we've done in 2020 on the BFS team, we transitioned over to using CCDD version 2. Really, that only affected the way commands were defined. We've transitioned all of our table management to use CCDD. And so, again, each custom app and also the core CFE apps, as well as sequences. So instead of sending one command, we can upload or issue one command that does a sequence of commands. And that sequence of commands is its own table that's stored separately. So those tables are all managed in CCDD. We have the data exports. And again, each of these is done by its own separate CCDD script. We can get the validation information for all of our table information. We can get the IDD information that we use to define all our interfaces to the rest of Orion, the header files that we use, the table files that we use, all the telemetry that we have that has CUIs. We can define all that, as well as we have a spreadsheet. So if we need to request additional CUIs, we can automate all the process of, or help automate the process of requesting new CUIs. We can automate the HK copy table. So we push a button and we get a new table. So we don't have to worry about changes. And then the crew displays, which are similar to the HK displays, HK copy tables. So all the team on BFS, all 12 apps were able to work in parallel and synchronize all their information into one common database. And just to give, I'm not going to give exact numbers, but we have over 20,000 lines of source code headers that are generated by the CCDD on the Orion BFS program, and more than 20,000 lines of config tables that are auto-generated from the CCDD. And just to put in comparison, if you count the quote-unquote hand-coded code that we have on BFS, it's less than 40,000 lines. So clearly, a majority of our code on the BFS program, if you count it just based on purely on lines of that are there, are from the CCDD. So we're making good use of automated tools for our code. So future work, some of the things we want to do, we're looking forward to the Artemis 1 launch. Hopefully there's no major issues or delays later this year. And then we'll be supporting the data management of Artemis 2 until it launches, hopefully sometime in 2023. And then in parallel, sometime this year, we'll probably branch off an Artemis 3 database for the CCDD, because there's slight changes in the vehicle configuration and some new capabilities are going to be coming online. So we'll have to define new messages and put those into the database. And also there's some vehicle specific calibration values that are going to change between Artemis 2 and Artemis 3. And so we're going to have a separate database to hold the Artemis 3 information. And then along the way, we'll be documenting our lessons learned and how this process has gone, so that future programs can learn and see how things went. And so the new features and updates that we've made to the CCDD for BFS are already available for other programs. And then also any comparisons that we can make with CCDD and Rhapsody, which is the tool the primary is using on Orion to do sort of the similar things to the CCDD. We can look at those things. So that's the end of the presentation, and I'll just leave some time for questions. If you guys have anything, feel free to contact me. Thank you.